Understanding the brain chemistry of depression and the molecular action of antidepressants requires delving into neuroscience and pharmacology. Let's break it down step by step. At its core, depression is believed to be associated with dysregulation in neurotransmitter systems, brain circuits, and neuroplasticity. Here's a closer look at the key players. Neurotransmitters play a significant role in depression. Serotonin, also known as 5-HT, is a neurotransmitter linked to mood, appetite, and sleep. Low levels are often associated with depressive symptoms. Norepinephrine, or NE, is related to alertness, energy, and stress responses. Reduced norepinephrine activity is also linked to depression. Dopamine, or DA, plays a role in motivation, reward, and pleasure. Dysregulated dopamine pathways can contribute to anhedonia, which is the loss of pleasure. Depression may involve changes in the sensitivity and density of receptors for these neurotransmitters. For example, the serotonin 5-HT1, a receptor is thought to play a crucial role in mood regulation. Overactivity of the amygdala, which is involved in emotion processing, and underactivity of the prefrontal cortex, responsible for decision-making and mood regulation, contribute to depressive states. Impaired connectivity between these regions disrupts emotional balance. Depression is associated with reduced neurogenesis, or the growth of new neurons, and synaptic plasticity, especially in the hippocampus. Chronic stress can shrink this region, affecting learning and emotional regulation. The hypothalamic pituitary adrenal, or HPA axis, is often overactivated, leading to excessive cortisol levels, which can damage neurons and inhibit neuroplasticity. Antidepressants aim to restore balance in neurotransmitter systems and improve brain function. Their action involves molecular interactions at the synapse. Selective serotonin reuptake inhibitors, or SSRIs, block the serotonin transporter, or SERT, preventing the reuptake of serotonin into presynaptic neurons. This increases serotonin levels in the synaptic cleft, enhancing its availability to bind to receptors. Over time, increased serotonin desensitizes autoreceptors like 5-HT1A, leading to a sustained boost in serotonergic signaling. Serotonin norepinephrine reuptake inhibitors, or SNRIs, inhibit both serotonin and norepinephrine transporters, boosting levels of these neurotransmitters in the synaptic cleft. This dual action enhances mood and improves energy, often addressing both emotional and physical symptoms of depression. Tricyclic antidepressants, or TCAs, block reuptake of serotonin and norepinephrine, but also interact with histamine, acetylcholine, and other receptors, leading to more side effects. Their broad action increases neurotransmitter levels but with less specificity. Monoamine oxidase inhibitors, or MAOIs, inhibit monoamine oxidase, an enzyme that breaks down serotonin, norepinephrine, and dopamine. This increases the availability of these neurotransmitters. Their potent effect can relieve severe depression but requires dietary restrictions due to interactions with tyramine. Atypical antidepressants include examples like bupropion, a dopamine norepinephrine reuptake inhibitor, and mirtazapine, an alpha-2 adrenergic antagonist that enhances serotonin and norepinephrine release. These target different neurotransmitter systems to tailor treatment for specific symptoms. Time-dependent changes. Antidepressants do not work immediately because they rely on longer-term molecular adaptations. Neuroplasticity. Chronic antidepressant use enhances brain-derived neurotrophic factor, or BDNF, promoting neurogenesis and synaptic plasticity, especially in the hippocampus. Receptor sensitivity. Over time, receptor density and sensitivity adjust, restoring balance in neurotransmitter signaling. Circuit connectivity. Improved neurotransmitter signaling enhances connectivity in mood-regulating brain circuits, reducing overactivity in the amygdala and enhancing prefrontal cortex function. Limitations of the monoamine hypothesis. While traditional antidepressants target serotonin, norepinephrine, and dopamine, depression is more complex. Glutamate and GABA dysregulation. Emerging research highlights the role of excitatory or glutamate and inhibitory or GABA neurotransmitter imbalances in depression. Inflammation. Chronic inflammation and elevated cytokines are linked to depressive symptoms. Individual variation. Genetic and epigenetic factors influence how individuals respond to antidepressants. Newer therapeutics. Modern approaches target additional pathways. Ketamine and esketamine. These NMDA receptor antagonists act on the glutamate system, offering rapid antidepressant effects by enhancing synaptic plasticity. Psychedelics like psilocybin modulate serotonin 5-HT2A receptors and promote long-lasting changes in brain connectivity. Anti-inflammatory agents aim to reduce neuroinflammation associated with depression. By acting on neurotransmitters, receptors, and brain circuits, antidepressants restore balance at a molecular level. Over time, they enhance neuroplasticity and brain function, alleviating depressive symptoms and promoting emotional well-being.